And we're going to use some statistics. First point is we can just take the mean value, or the average value. And if we take n measurements, we simply take and add up the n measurements and divide by n. We're going to call that the mean value. Straightforward. That is also called the average value. There are other measures of central tendencies, which we will refer to but will not use. If you're taking statistics, you may well run across these. There's the median, which is the midpoint of the data, so half the data is above and half the data is below. And sometimes that's useful, particularly in economics, but in physics we usually don't use medians. The other is the mode, which is the most common value. For our purposes, that will be completely useless, particularly since most of our data will be randomly distributed and we'll be using metric data, and chances of getting the same value over and over again are pretty small. When you measure the period of a pendulum, for example, it's very unlikely you'll get exactly the same time more than once. So the measure of central tendency that we're going to be using will be the mean value. However, all the x's will not be the same. They'll be distributed. And a measure of how far they vary from one another is called the standard deviation. Not really going to worry too much about why the standard deviation is defined as it is, except to note that we take an individual value, we subtract the average value, and then we square it. We square it so that we're counting numbers that are too big the same as numbers that are too small, so that the ones too big here are not going to cancel out the ones that are too small. It's just measuring how far you are from the average. Note, you might say, well, why don't we just use the absolute value? And ask your statistics teacher, because that's the reason why. It provides better statistical information. And then we take effectively the average value of that, but notice we're going to divide by n minus 1, not n. There actually are two definitions for standard deviation. One you do divide by n, and one you do divide by n minus 1. One is the standard deviation of the population, and one is of the sample. We're not going to worry about that right here. All we're going to worry about is the fact that you use the one that's the n minus 1. So when you do these calculations on, for example, your calculator, it will actually give you two values for the standard deviation. We're always going to want the larger of the two because it's divided by the smaller number. So that is just a measure of how much your data varies from trial to trial. However, that's actually not quite what we want, because this is on a given individual measurement, and that variation will be determined by the instruments that we use and the procedure that we use. What we really want to know is not how much does the data vary, but how good is this average value right here, which uses all of the data points. Namely, if I repeat my experiment over and over again and make, say, n measurements, have I picked n large enough for having all of the large numbers counterbalanced by all of the small numbers so I get a very good average value? Or, if you will, what we want is the standard error, or what is also called the standard deviation of the mean. To do that, what we do is we take the standard deviation, we divide by the square root of the number of samples. So the more samples we take, the better our average value will be. Now, what this alpha means is that take an experiment. Experiment, for an example, could be you measure the period of a pendulum using a stopwatch, and you measure it 15 times. That's your experiment. You do that, you get an average value right here, you calculate your standard deviation, and from that you compute the standard error. What this standard error says is that if you repeat that experiment, measuring the same pendulum, the same stopwatch, for the same number of times, how much will that mean value change? Because you're not going to get the same mean value, because you're not going to get the same data set each time. Alpha will get smaller the more measurements you take, because the more of this variation will get averaged out and the mean value won't change as much. On the other hand, if you designed your experiment differently and decided you were only going to take 2 measurements of the period, then you're going to find for that experiment the mean values are going to change much more from time to time, because you didn't take enough measurements to average out the variation. So what we really want to find out is what is alpha. We're going to use alpha to find out how close our mean value is to the true value. So we're going to do this by stating the mean value plus or minus alpha will be how precise our measurement is. The smaller alpha is, the more measurements we've taken, the more precise our average value will be. And we're going to use alpha to determine how many sig figs we cite on our mean value. The way we're going to do that, we'll show some examples in a moment, is we're going to cite alpha always, this is just an internationally accepted standard, to 2 sig figs. Take the smaller of the sig figs, the last sig fig in alpha, that determines the last digit that you cite in the mean value. I know that's going to be a little confusing, so to do that, we need to do some examples. And before we do the examples, I just want to highlight one thing which you've probably run across in the difference between accuracy and precision. Note that's a distinction people make in high school. You may run across it in college. Actual scientists will not make this distinction. Accuracy is supposedly how close you get to the true value, and precision is a measure of reproducibility. How consistent are your results? And the reason real scientists don't use this distinction is that it presumes you know what the real value is. Well, if you're the first person doing the experiment, the first person making a measurement, you're doing real original research, you have no idea what the true value is. Therefore, you can't estimate what the accuracy of your measurement is, because this true value is completely unknown. You can, however, talk about the precision of your measurement, because that's its reproducibility. You can do your experiment over and over and over again and find out how close you got. But you really can't talk about accuracy. Still, since we will be doing experiments that have already been done, we're reproducing other people's, we can say what the accepted value is. Sometimes this is a difference between experiment and theory. Note the question really is, are you testing the theory, in which case it's the experiment that's accepted and the theory is what you're questioning, or do you have a well-established theory and the question really is how good was your experiment at testing the theory, but the theory is already well accepted, in which case the experiment becomes the thing that you're questioning. So this formula right here is a bit arbitrary. Real scientists don't use this. They don't talk about this. This distinction is one that we will make here, and it is useful for our purposes, but real scientists don't worry about that. Now let's do an example. Here I have some simple data. I've got Al, Beth, and Carl all making measurements, and here's their data. I want you to do some calculations, and if you want to figure out how you do these, I have posted a video on how to compute means and standard deviations using your calculator, and there's also a handout. So I would suggest looking at those as you do these calculations. What you're really going to do is enter these values right here into a list, and then just use the stat calculations on your calculator. When you do that, which I would suggest taking a pause and doing that, we'll find Al's results. We take the mean value for Al, and that turns out to be 23.16, and I'm only going to cite 2 digits at the time being. We calculate his standard deviation, it's 3.10. Take this number and divide it by the square root of 3. That'll give me the standard error. So now we've calculated the 3 numbers, the mean, the standard deviation, and the standard error. Now, convention. Standard error is cited to 2 sig figs. So we're going to call this just 1.8. So there's our standard error, 1.8. We then cite the mean value to the last digit of alpha. Well, that's the tenths place, the 0.8. So therefore, we take the mean value and we round it off to the tenths place. So we cite this not as 23.16, but as 23.2. Al can only cite his results to 1 decimal point. And that's because his numbers varied a whole lot. Note, the first digit right here, the 2, did not vary at all. So everyone's going to agree that, yes, the first number is 2. Second number varied quite a bit, from 0 to 6 to 2. So there's uncertainty in the units place. In addition, there's uncertainty, therefore, in the tenths place and in the hundredths place. Now we're just talking about convention. Internationally accepted convention is you only cite the last two uncertain digits, which in this case would be the units and the tenths. So Al did not design a very good experiment. His results varied a whole lot, so he can only cite his results to the tenths place. So that's doing it for Al. We do the exact same calculation for Beth. So enter Beth's numbers into a list and do the calculation. And we find out that Beth's average is this number, her standard deviation is this, and her standard error is 0.05206, which is just the standard deviation divided again by the square root of 3. So we take alpha, we round that off to 2 sig figs, which is 0.052, and there's our alpha. The last digit in alpha is the thousandths place. That means Beth gets to round off her mean value to the thousandths place. So her mean value is 19.027. Notice she actually gets to cite one extra digit than she even measured, because she actually wrote down the results. These could be results perhaps from a stopwatch, which measured hundredths of a second. Because her results were so consistent, she actually gets to interpolate between two measurements. Now this may sound kind of weird, but it's perfectly acceptable. Let's assume you did a time and you always got 1 and 0.99. Those are the only two numbers you got, and you got half of them were 1 and half of them were 0.99. It would seem quite possible the actual time is 0.995, halfway between those two measurements. You didn't measure a thousandths place, but your results suggest that the time is halfway in between those two values. It's kind of like what Beth got right here. Because her results are so consistent, she can actually cite an extra digit. So her results are certainly more precise than Al's. Now let's consider the last one, Carl. Do the same calculation for Carl, and here we get his mean, his standard deviation, and his standard error. And the standard error is 0.040, so that is his alpha, and his alpha's last digit is the hundredths place, so he has to round off his result to the hundredths place. So this is Al's. This is Carl's. Now we can discuss a little bit the difference between accuracy and precision. Now here we don't know what the true value is. That's what I started right here. There's no true value. So we really can't, as we usually often can't, discuss which one is more accurate. However, if we look at Al and Carl, they're both fairly close to each other. Namely, they're numbers that are a bit over 20. Beth's is consistently under 20. So this would tend to suggest that Al and Carl are consistent, so it's more likely, if you will, the so-called true value is closer to their averages. Now, Al's average was 23.2, and Carl's average was 24.07. These two are fairly consistent with each other. Beth's is noticeably far off. It's 19. So probably what we're seeing here is Al and Carl got closer to the real values. They're more accurate. And Beth is noticeably off. She's probably less accurate. She may have some sort of systematic error in her measurements. However, hers are certainly by far the most internally consistent, so she is certainly the most precise. So Al has a lot of random error in his measurement. Carl less so, and Beth much, much less. So Beth has the most precise measurement.